Hi there, we're going to look at some forces on a slope type questions today, and not unsurprising, we've got a skier coming down the hill. I suppose skiing's great because there's very little friction to worry about, so you can always assume there's no friction, and you always get, as I say, questions where you're going downhill, so and uphill when you're going up in the lift. So it's quite common to see these questions, and other reasons why we have questions on a slope as well. So let's have a look at some things first of all. Now, as a starter, I want you to think about the forces which act on this particle which is going, well, sitting there on the slope. Now, weight obviously acts straight down. That's known to be true, and of course we know that weight equals mg. But I suppose what is more useful is when you consider what the effect is of this weight as it acts either parallel to the slope or perpendicular to the slope, because that's invariably when we get these questions we have to resolve the weight, and when we resolve the weight we can actually then rewrite these in a more friendly version. So first of all, if this is 30 degrees there, I just want you to realize this is a right angle triangle. This up here must be 60 degrees. And this up here is also 30 degrees because this is a right angle triangle. So if I resolve this weight, which is presently going straight down, but in this direction, I could write this as, well, the weight, or I'm going to call mg. And because it's cos, and that's there, I could resolve it as cos 60. And the only thing I don't like about this is mg cos 60 is it's not the angle they tell me in the question. Almost always they tell me this 30. I don't really want to change it. But the good news is I can cross this out, and because I know that mg cos 60 is the same as mg sine 30. And they're the same thing. And likewise, this one, you'd normally call this force going in this direction, you'd normally call it mg, well, sine 60. And again, I don't like this fact it's sine 60 because the angle is 30, they tell me in the question. So again, you can rewrite this as mg cos 30. And if you just check on your calculator, cos 30 and sine 60 the same, sine 30 and cos 60 the same, and that fact allows us to resolve it in these two directions. This becomes incredibly useful when you resolve in the direction of the dotted lines, as I called it, parallel and perpendicular to this slope. Forces acting on a slope then, and this is, if you like, the posh version of it, and we've got the weight. Oh, that's one which I've not yet considered. Bear in mind that we also have this normal contact force called the reaction force acting on the skier in this case. We have some friction. How much is debatable, and he's moving downhill, so therefore you can see the friction's going uphill. And the direction of these forces matters, and of course what I'm saying to you is just be aware this W doesn't have to be thought of as W. If you think of it straight down, that doesn't go the same way as the R and the F. So that's why it's much better to resolve it this way and this way. And then it's in the opposite directions to the R and the F, and we can compare them. So mg cos theta, mg sine theta. Now I've said this is 30, but of course it works for any angle. Just bear all that in mind when you're doing questions. So if there are forces in equilibrium, i.e. for instance it's moving at a constant speed, or perhaps it is sitting there at rest, then you can say the F is equal to mg sine 30, left equals right. And if it's, as probably not the case, he's not jumped up and down on the slope, so R is mg cos 30. Now even if there is some acceleration, you can use F equals ma. And this is F equals ma, but you'll notice he's moving down the slope, for instance, so that force is going to be bigger than that force, or else he wouldn't be moving. Mg sine 30 minus the friction is equal to the mass times acceleration, assuming he's accelerating down the slope. So let's do a couple of questions and to get our head around this. The first one, it says find the coefficient of friction. Of course we know the coefficient of friction is found by using this F equals mu r formula. A block of mass 2 kilograms, so that's 2 kilograms, rests on a rest tells me it's not moving, it's left equals right, up equals down, on a rough plane, so there is friction. But I suppose the one way I think about this is it's trying to go downhill, and the reason why it's trying to go downhill is that force I just talked about, mg sine 25. And again, I can write into the slope, I can write mg cos 25. Okay, what was I saying? So it sits on a rough plane, so there must be some friction. And there must be a normal contact force or the reaction. And it says find the coefficient of friction between the block and the plane if the block is about to slip. So it's on the point of moving. So therefore F equals mu r is the right equation to use, rather than less than or equal or something like this. But F equals mu r then, can I work out my r? Well, yes I can. Up equals down. So r is equal to mg cos 25. Which in this case is 2 times by 9.8 times by cos 25. Now you can type that into your calculator, and I get 17.76. I'll give one extra decimal place just in case I need it later on. 17.764 newtons. So now I know my r, of course. I can now work out my constant of coefficient of friction. Now you might be thinking, well, how can I do that? Well, I also know something else, you see. It's at rest, so this equals this. So my second statement is that my friction is equal to mg sine 25. Left equals right. So again, I do the same thing. It's 2 times 9.8 times sine 25. Let's do that out. 2 times 9.8 times sine 25. And I get 8.28. Well, 283. Again, extra decimal place just in case I need it. Well, again, I'm now in a position where I can use my formula F equals mu r. So I can say F 8.2893 is equal to, the formula says mu r, so mu times by 17.764. Or put a different way, mu is 1 divided by the other. Let's just do that. Divided by 17.764. I left a whole number on my calculator. Oh, 0.46 in a bit. 0.466. That's my mu. If instead the coefficient of friction is 0.4, alright, so for some reason they've decided to change mu, find the magnitude of the acceleration. Well, I suppose it's the same idea though, isn't it? The great thing about what we've just done is mg sine theta hasn't changed. That's the same. The r hasn't changed because that's equal to mg cos 25. The only thing that's changed, I suppose, is this coefficient of friction. And because the coefficient of friction has changed, the friction here, I suppose, has changed as well. And what that has meant is it starts to accelerate. There is less friction, therefore it's willing to accelerate. So let's just do this on the next page. We had before, let's just remember, the R was 17.764. That's not changed. My mg sine theta, whatever that was, hasn't changed. That's my 8.293. So I've still got 8.293 coming down the slope. But because my mu is now 0.4, I can now work out my friction again. And my friction now is F equals mu r, which is these two times by each other, 0.4 times by 17.764. And I get 7.1056. You can see now this 7.1056 is lower than this 8.293, and that's why if I do effectively an F equals ma going down the slope, I've got 8.293 minus the 7.1056 is equal to the mass times acceleration, the 2 times the acceleration. So I can take away one from the other. 8.293 minus what I just got is 1 and a bit, 1.1874 equals 2a. And so when I divide that by 2, I will get my acceleration. And it's 0.594 meters per second squared. And that's right. So on that basis, let's do the next one. Oops, what's going on there? A child of mass 30 kilograms is pulled up a rough ski slope. So he's being pulled up. So bear that in mind, because he's being pulled up, we know, lost my pen, we know there's friction pulling them back down again. Assume it's a rough ski slope, which it says it is. And there's not only just friction, there's also the weight in that direction, and we know that's mg sine 20. It's always sine parallel to the slope, and it's always mg cos theta, or in this case 20, perpendicular to the slope. What was its mass? 30. Don't forget also we've got the reaction, the normal contact force. Now all these things comes into play. We know as well that we've got an acceleration, normally drawn with a double arrowhead. It says create an acceleration of 0.25. A equals 0.25. And what else have we got? The coefficient of friction is 0.2, so we know that mu equals 0.2. So all of this. Now, all of this is going to be important, but the first thing I'm thinking is let's calculate what these two things are. So mg cos 20 will be r. So let's do that straight away. R equals mg cos 20. So I'll need to time that in. What was m? M was 30. So it's 30 times 9.8 times the cos of 20. And that's 276-ish. 276.27. And we also know what we've got in this one is being accelerated, so it's not a case that they're equal to each other. But we do know that F equals ma will apply. Now, in order to do that, I'm going to need the friction first, actually, and I can get the friction. F equals mu r, and I know mu is 0.2, so that number I just worked out is now going to become useful. So times that by 0.2, 55.25. And so we can now write that T, I'll do what I'm going to do. The thing I'm going to do is F equals ma, and I'm going to do it on the next slide. F equals ma, of course, you can use whenever there's motion, there's acceleration up the slope or down the slope. So I'll do it here. So we've got a T minus, we had these two forces coming off. Then we had a friction, which we just calculated to be 55.25. And we also had an mg sine 20. I suppose I haven't worked that out yet. What is mg sine 20? Well, it is definitely 30 times 9.8 times sine of 20. And I get 100.55. Now that mg sine 20 then comes off the tension as well. And all of these things effectively slow down the rate of acceleration from the buoy up the slope. And that equals the mass times the acceleration. The mass is 30. And we're told the acceleration from memory is 0.25. Let's go back and check that. Yes, 0.25. So it looks like we can find T. I reckon work that out, work all those out, and move everything around. I'm adding on the things as I move them over, obviously, and I get 163.3 newtons. So I'm not sure if there was a part B to the question. No, that was it. 163 newtons to 366. That's right. And we're running out of time, really, and I'll save a couple of questions for you to have a look at in class, and it's always nice to have a couple of questions. But obviously you'll build on what we've done. Just remember a couple of things here. We've got a ski of mass 80 kilograms in limiting equilibrium. That basically means he's on the point of accelerating, but effectively it means that all those left equals right, up equals down things I was talking about before is going to be true. So it says find the magnitude of the frictional force and the normal contact force. So, well, the normal contact force will be equal, as in before, to its weight. Up equals down, if you like, perpendicular to the slope. Now, the skier is going downhill. So he's trying to go downhill. So we've got one thing pulling him downhill, and that's mg, in this case, sine 7. And going up the hill is his friction. So you can effectively, we're going to use these, but I'll leave that till the class when you do it in class. And it's quite a nice topic, this, to be honest. I quite like it. So in class then we'll try and get these kind of questions done and have a look at exercise 21C1 you're in class. So thank you very much.